So on to the second law, okay? So first law was that we can't create or destroy energy. We can only have energy transformations. And the second law is that those transformations always have directionality, okay? And we know which way they're always going. So every time anything at all happens, energy and matter are going to be changed. Okay? Most of the study of thermodynamics as a field was based on studying steam engines and then later internal combustion engines. If you take sort of a mechanical or chemical thermo class, you'll talk about Carnot cycle, you'll talk about refrigeration cycles. We are going to talk about them not even at all, super briefly. And then we're going to talk about a statistical definition of entropy, because what we care about is what a million biological molecules are doing inside of us, as opposed to from sort of a macro scale what's happening. Okay, because we already said inside our pressure is staying the same, our volume is staying the same, so we're not really interested in big mechanical movements and stuff like this. Okay. So in this situation here, though, we have coal combusting. Okay, we're heating up the water. As the water heats up, it turns into steam. We have this phase transition. The steam wants to expand. Okay, the expansion of the steam comes around, pushes this piston, and it moves the wheel doing mechanical work. Okay. All the energy that we have in the universe is staying the same. It's just changing. Is it mechanical work? Do I have heat energy? Was it chemical energy? Was it what was stored inside of the coal? Right? And second law is those changes have direction. Energy isn't going to flow back out of the water and back into the coal. We can't go backwards in this case. Okay? And so that direction is always towards maximum entropy. Whatever would create the most dispersion, the most disorder, whatever direction raises entropy is the spontaneous direction that I want to move towards. Okay? And I mean, in a very oversimplified way, that kind of makes sense here, going towards, we know that steam is more random, it's going to expand more, all of these transformations are going in the direction that makes sense for us logically. Okay? Okay, so the second law of thermodynamics, there's a ton of ways to say this. Okay? One of them is this idea here. It's the maximum entropy principle. It's everything's tending towards maximum entropy is one way to say it. I'm going to put like 6 more ways to say it up on the screen. Okay, there isn't like one maybe super nice way. For a system that is not at equilibrium, the direction of spontaneous change would be towards maximum entropy. That's one way you could say the second law. Right? So if you have, again, sort of one way to think about it is it's more likely that bricks would fall in a random pile than nice and neat. Or we know that, if you have 2 materials, they're going to want to mix together and disperse. Okay? Maximum entropy is the most likely or the most probable state. Okay? We're going to start talking about probability shortly. So, and this is at equilibrium. So once we've reached equilibrium, all of our macro properties aren't changing, temp, pressure, volume, internal energy of our system, nothing's changing. We would expect it to have tended towards max entropy. And if I'm at equilibrium and I want to get away from it, I'd have to put energy in to do it, okay? And so that's kind of obvious here too. If I'm in this state and I want to go back to sorting these 2 things, it's going to take energy to do so. Okay, it's not going to happen on its own. Same thing here, I'd have to put in some energy to line this all up. Okay. So if you're sort of at your high entropy, spontaneous state, once you've reached equilibrium, if you want to go anywhere else, you'll have to put in energy. And the overall entropy of the universe is always increasing because absolutely no energy transfer is ever 100% efficient. You can never turn 100% of heat into 100% work, ever, okay? We'll always have these heat losses to the environment, heat or other types of losses to the environment, right? Okay. So that's this part here. Here's the maximum of work we could do. If we could have a true reversible case, nothing's reversible in real life. So the difference between these 2, or whatever this might look like, we're going to have some kind of losses. So one way to maybe think of entropy is sort of like energy you can't get back, energy you can't do anything with, right? You can't turn that vibration or heat or sound back into anything, potentially. Do you guys want to watch this video? It's like 1.5 minutes long. It's narrated by Morgan Freeman, and it talks about how like everything's gonna die. Okay. Last semester, I had a link that was valid, and then it was no good anymore. It was like broken YouTube. And so I say like, oh, hey, if anyone finds this, send it to me after class, and I'll give you extra credit. And of course, like 2 people emailed me within 3 minutes of me lecturing. I'm like, okay, you're supposed to pay attention. But... All right, so let's see.
A theoretical physicist at City College of New York is fascinated with the big questions.
Can we hear it?
Like whether the laws of physics require that all living things die.
One of the iron laws of physics is the second law of thermodynamics, which says that everything rusts, everything decays, falls apart. We're all made out of atoms, and these atoms in turn obey the second law of thermodynamics.
Anything and everything in the universe has the tendency to go from order to disorder. And once the damage is done, it's extremely difficult to reverse things and unmix them. It's a process known as entropy.
If I mix coffee, I realize that when I put cream into coffee, I increase entropy, I increase disorder. In fact, to see this milk jump out and reform in this cup is such a preposterous event that you would have to wait longer than the lifetime of the universe to see it happen.
The second law of thermodynamics is an unremitting force. Nothing is immune to the power of entropy, not even the cells in our body.
And that's why we age. In fact, that's why we die.
So again, everyone likes to think that what they teach is the most important thing. Since entropy is why we die, you're welcome to the most important class you're ever going to take. Here it is. I actually didn't realize I forgot that video talked at all about coffee and creamer mixed together, because if anyone actually read their homework, that is one of the questions. And I did not realize it was in this video. That's okay. It asks you about some other stuff besides just entropy. Okay. So, a couple more, some of these statements I might have said already. If not, a couple different ways to say the second law. Combined entropy of a system and its surroundings, which makes up the universe, okay, those are only 2 parts, always increasing. You can never get an equivalent amount of work out of a given amount of heat, right? No energy transformation will ever be 100% efficient. And all energy transformations move in the direction that would maximize entropy. And like I said, we'll see these a couple more different ways. They'll reappear on slides as we go.